we're going to talk about describing data.
Here's chapter 3, describing, exploring, and comparing data.
The following data gives the number of hours that a few employees at the GM factory worked last week: 17, 38, 27, 14, 18, 34, 16, 42, 28, 24, 40, 20, 23, 31, 37, 21, 30, and 25. Find the mean.
Here's the formula that we need to use for the mean. And before we do that, I like to rank the data. Bear in mind, we don't need to rank the data to find the mean. So it's important to pay attention to that. However, because we have other parts that they definitely need ranking, in order not to take a chance, I am ranking them. So X bar by definition is summation of X over N. Why am I using X bar? Because I know I'm dealing with a sample, just a few employees. That means it's a sample. X bar is summation of X over N, which means simply put, add them up, divide by size. And that gives us the answer. As far as the number of decimals, you want to pay attention to what they ask you to do, just to be on the safe side. The next one is asking for the mode. There is no mode. Why would that be? Because mode, by definition, is the one with the highest frequency of occurrence. No repeat, therefore no mode. None of the numbers repeat. Find the median. The median is basically the middle of the data. In this case, we are dealing with an even number, which is 18 pieces of data. So we add up these two numbers right in the middle, 25 and 27, divide by 2, and that is the median. The next one is the mid-range. By definition, mid-range is the max and mean divided by 2. Mid-range is the value midway between the max and mean. So you add up the max and mean. And I hope you realize for the mode, median, mid-range, all of them, we do need the rank data. That's why I did it in the first place, not to take a chance. So obviously the largest value is here, 42. The smallest is 14. Add them up, divide by 2. The next part is asking to find the range. By definition, range is max minus mean. So 42 is the largest number, 14 is the smallest one. We end up with 28. It's important to realize normally range and mid-range are not the same. It just happened by chance in this calculation. We are going to calculate the variance and standard deviation. We already have the data from the previous page in ranked format. We calculated the mean or X bar. So we are going to calculate the standard deviation and variance by using the sample variance formula. It's important to pay attention. This is dealing with a few employees, and that makes it a sample. Therefore, here's the variance. There are two different formulas, and I'm going to show you how to use them. Needless to say, for a large data, obviously you can use technology. But at the same time, I want you to be exposed to the methodology as to how it's calculated if you have a small data and you want to do it by hand. You can do it this one, use this formula or this one. I'm going to show you quickly both of them. So speaking of the second one, here's the S squared. N, we have 18 pieces of data. Summation of X squared means add them up, 14 plus 16, all the way to the last one, 42, and square them. So 14 squared, 16 squared, 18 squared, all the way to the last, minus summation of X, quantity squared. Now you have to individually add them up. That means 14, 16, all the way to 42. That means individually add them up, then square them. So in essence, it's the order of operations. And the denominator is n times n minus 1, 18 times 18 minus 1. You calculate it that way. again, if you were to do it by hand, if we were to use this formula, what this means, summation of x minus x bar quantity squared over n minus 1, what that means is that each individual piece of data, in this case 14 for the starting one, minus x bar, which is 26.944, and square it, plus then the second one minus that, so on and so forth. So 14 minus the x bar squared, and then 16, 17, 18, all the way to the last one, 42 minus whatever the value of x bar is squared divided by 18 minus 1, and they both give us the same answer. That's as far as the variance is concerned. What about the standard deviation? When you get the variance, all you have to do, take a root. So here's the formula, but you don't want to go through the process again. You already have the variance. Take a root, again, a higher number of decimals they ask you. We want to find IQR, also known as inner quartile range. So IQR describes the middle 50% of the data, and by definition is Q sub 3 minus Q sub 1. When we cut the data into 4 equal parts with 3 values, Q sub 1, Q sub 2, and Q sub 3, where Q sub 2 is the same as the median. In order to find Q sub 1 and Q sub 3, you could use various methods. I'm going to go over one easy way. First and foremost, we found the Q sub 2 by finding the median, which was right here, 25, 27, add them up, divide by 2. The other one is that you can cut the data into the first half and the second half. The first half has a median. That's number 20. That's why it's the fifth one. The second half, starting from the 10th one, also has a median, number 14, which is 34. So you have Q sub 2, the middle of the data, Q sub 1, the median, they can call it sometimes submedian, or the median of the first half, Q sub 3, the median of the second half. I will explain different methods to calculate that in a moment. So inner quartile range, by definition, is Q sub 3 minus Q sub 1, and that would be 34 minus 20 makes it 14. IQ scores have a mean of 100 and a standard deviation of 15. We want to find the coefficient of variance. First and foremost, anytime you deal with stats, in essence, you're dealing with word problems. So what is given? Symbolically, mu equals 100, sigma equals 15, because we are dealing with the population. We're not going to use X bar and S. We are going to use mu and sigma. Coefficient of variance has a specific definition, describes the standard deviation relative to the mean, and is used to compare the standard deviation when the units are different. So in this case, sigma over mu times 100%. This one is just to change it to a percentage, because normally we use percentage to represent a coefficient of variance. But for all practical purposes, you calculate this fraction. Now you simply plug in and you change that to a percentage. The answer is 15%. Coefficient of variance. Next comes range rule of thumb. We want to use the range rule of thumb to estimate the minimum and maximum usual IQ scores. By definition, range rule of thumb, mu plus minus 2 sigma, or X bar plus minus 2S. In other words, the range rule of thumb says you start from the mean and you go 2 standard deviations to the right, 2 standard deviations to the left, and that would be considered the usual. So mu plus minus 2 sigma, mu is 100, sigma is 15. So 2 times 15 is 30, subtracted from 100 becomes 70, added to 100 becomes 130. Therefore, according to the range rule of thumb, the minimum value would be 70, the maximum value would be 130, which means that would be the range for 2 standard deviations being away from the mean on both sides. We want to use Chebyshev's theorem to find what is the least percentage of those who will have an IQ score of 70 to 130. We want to do the same thing using empirical rule. So I wanted to compare and contrast the two. In the case of empirical rule, you know that you're dealing with a bell shape. In the case of a Chebyshev's theorem, you don't know about the shape of the data. So this is more conservative in that sense. So we already know from 70 to 130, it covers 2 standard deviations. Therefore, as far as the Chebyshev's theorem is concerned, we have 1 minus 1 over k squared. So the proportion of values from any data set that fall within k standard deviations of the mean. That means how many standard deviations over k? That means 1, 2, 3, 4, however many. It's given by the formula 1 minus 1 over k squared, where k is the number of standard deviations. In the case of a Chebyshev's theorem, we cannot use k equals 1. As you can see, if you choose k to be 1, 1 over 1 squared is 1, 1 minus 1 makes it 0. So with that being the case, we are going to use 2 here. Obviously, I mentioned as to why from the previous part, we know that k is 2. Therefore, 1 minus 1 over 2 squared. 1 over 2 squared is 1/4. 1 minus 1/4 is 3/4. So at least 3/4 or 75% have an IQ between the two numbers. Now, before I move on to the last part, I want to show you, in case we didn't know it was 2 standard deviations away, how would we figure out the value of k? If we don't know that, we put the mu in the middle, which is 100 here. And then we put the values 70 and 130 on sides. And we look at this distance, also this distance. As you can see, they are both 30. So they are away from the mean by 30 units. It becomes how many standard deviations in essence? Look at the standard deviation being 15. So number 30 means how many of those? In other words, divide this by 15, and that means 2. In order for you to find k, you divide this by sigma, which is 15, and you get 2. By the way, these two numbers must be the same. This in case we don't have the number of standard deviations as part B gave us, and we have to do it on our own. Now, as far as the empirical rule, first and foremost, let me just erase that. In essence, empirical rule is the same as the range rule of thumb. So within 2 standard deviations, it covers about 95% of the data. If you look at this drawing, we start from the mean and we go 1 standard deviation away from the mean. On each side, it covers about 68%. If we start from the mean and we go 2 standard deviations, this is about 95%. And if we start from the mean and we go 3 standard deviations on each side, it covers almost everything, 99.7%. We already know that we are 2 standard deviations away on each side, therefore, it's 95%. Empirical rule. This works when it's bell-shaped and symmetric, and we deal with that later on when we go over normal distributions.
Given the data 32, 19, 14, 7, 15, 3, 4, 5, 9, 16, 15, 16, 19, 50. A. Rank the data from smallest to largest. B. Prepare a box and whisker plot. Box plot.
So we rank the data. In stats, most of the time, it's really a good idea, even if they don't tell us to rank the data and work with it. So when we rank the data, it makes life easier. The next one is to prepare a box and whisker plot. By definition, a box and whisker plot needs a few pieces of data, the minimum, the maximum, and Q1, Q2, Q3. So we want to find all of those. So first and foremost, here's the bottom half, here's the top half, and if I want to find the median, just add up the middle data and divide by 2. I'm going to discuss the locator in a moment. But for now, there are different ways to find Q1 and Q3. So the median, it's always the easiest one, the middle of the data, the middle of the data. If it's even, add them up, divide by 2. If it's odd, you have one number in the middle. This is even, add them up, divide by 2, so that's 50. As far as Q1 and Q3 is concerned, I've already told you the methodology that you cut it in half, and median of the first half is Q1, median of the second half is Q sub 3. We also have this locator. Ultimately, there are different approaches. There are even a weighted average approach. But as far as the locator is concerned, remember, when we say Q sub 1, it is separating the bottom 25% from the top 75%, which means you basically have to look at the number of data and multiply it by Q1, the representation, which is 25% or 0.25. That's what this formula says. So you don't want to be confused by the formula. Basically count, that's N, for Q1, multiply this by 0.25 or 25%. Now, if you want to go with the locator, the way it works, you calculate 25% of N, and if it's 3.5 or 3.1, or it doesn't matter, as long as it has a decimal, you round up to the fourth one. So you're looking for the fourth piece of data, 1, 2, 3, 4, and it becomes 7. Now, bear in mind, in this case, if you look at the bottom half, the median is also 7. It doesn't work out like that always, but it works out here just the way you see that. For Q sub 3, you have to multiply by 0.75. So we're going to multiply N, which is 14, by 0.75 or 75th percentile in essence. That gives you 10.5. You go to the 11th piece of data, which is number 19, and that becomes Q sub 3. Also, it is the submedian, if you will. They also call it the second submedian or the median of the upper half. The way the whisker plot works, you come up with a number line, and on a number line, you put the minimum, Q sub 1, Q sub 2, Q sub 3, maximum. Now, for Q sub 1, Q sub 2, and Q sub 3, you make up a box. Like, that's why it's called whiskers and box plot, or box and whisker plot. All right, we want to find outliers. We are continuing with the same question. We already found the value of Q sub 1, Q sub 2, and Q sub 3. And we are looking for outliers. In short, the meaning of outlier is something that it's way beyond what we like it to be as far as the data. But specifically, statisticians give it a definition for that as follows. The values for Q sub 1 minus 1.5 times IQ sub R and Q sub 3 plus 1.5 times I Q sub R are the fences that mark off the reasonable values from the outlier values. Outliers lie outside the fences. In other words, you know Q sub 1, you know Q sub 2, and Q sub 3 from the previous page. We are going to calculate IQR, which by definition is Q sub 3 minus Q sub 1. Then we want to multiply that by 1.5. And the result we subtracted from Q1, Q sub 1, we also added to Q sub 3 to find differences. Any number beyond those is considered an outlier. So Q sub 3 minus Q sub 1 results in 12. When we multiply it by 1.5, results in 18. So now Q sub 1 is 7 minus 18. And Q sub 3 is 19 plus 18. So according to this data, Q sub 1 minus 1.5 IQR becomes 7 minus 18, which is negative 11. And if you add to it, becomes 37. Therefore, number 50, which is larger than 37, is an outlier. So you want to make sure to justify your answer. Do we have an outlier? Yes. Why is that? This is the process. Sometimes they are also interested in an extreme outlier where they use, instead of 1.5 times IQR, 3 times IQR. In case anybody is interested in Q sub 1 minus 3 times IQR, which means 3 times 12 equals 36. So 7 minus 36, and it makes it minus 29, 19 plus 36. And as you can see, we don't have an extreme outlier because the largest number is 50. This is 55. All right, we want to see whether this is symmetric or skewed, and we need to pay attention to a few notes. Before we answer the question, there are 3 notes coming up.
Note 1, make sure the drawing is to scale. Note 2, skewed data show an uneven box plot, in which case the median cuts the box into 2 unequal pieces. Longer part on the right or above the median indicates data is skewed to the right, positive skew. The mean is greater than the median. Longer part on the left or below the median indicates data is skewed to the left, negative skew. The mean is less than the median. Note 3, sometimes the box may look even or uneven and even skewed to one side. However, the whiskers, tails on each side of the box, may indicate otherwise. Therefore, pay attention to both.
So the idea is that you want to be very careful when you want to answer that question. So one way that makes it easy to understand, if you draw this line at the bottom and the Q sub 2 and see which one is longer. Obviously, the right side is longer. Therefore, it is skewed to the right. They also call it positive skew or positively skewed. Either way is fine. We are going to do the same thing here with this data, coming up with the box and whisker plot. First, let's cut it in 2 pieces. And as you can see, for the median, we can add up 86 and 87. There are several methods to do that, but the easiest way is this way, as far as the median is universal, but the Q sub 1 and Q sub 3. So stick with this method. Obviously, add them up, divide by 2. That's Q sub 2. Again, there are different ways to calculate Q sub 1 and Q sub 3, but we stick with the easy way out. We have the bottom half and we have the top half. And we come up with the median for the bottom half. That means 79 and 80 divided by 2. And for the top half, 87 plus 94 divided by 2. When we add up those 2 and divide by 2, we end up with 79.5 being Q sub 1, 90.5 being Q sub 3. Again, you could use the locator and you'll see that you may get a different answer. However, this is the general form to calculate this. As far as the 5-number summary goes, we have the minimum, we have the maximum, and now we got Q sub 1, Q sub 2, Q sub 3. So you draw a number line, if you will, and you tick mark the mean, Q1, Q2, Q3, and max. So you tick mark those values. And for Q sub 1, Q sub 2, and Q sub 3, you make up a box. So take a look. So you have a number line, you check mark those 5 values, and you make up a box for Q sub 1, Q sub 2, and Q sub 3. And bear in mind, Q sub 2 is the same as the median. Now, if anybody is interested and the question didn't ask us, you can calculate the IQR multiplied by 1.5, which gives you 16.5, subtracted from Q sub 1 gives you 63, added to Q sub 3, which gives you 107, and you know the fences and the numbers beyond those numbers are considered outliers. As far as extreme outliers, as I mentioned, you have to multiply the IQR by 3. Notice when we draw this line, it seems that they're almost identical, maybe a tad to the right, but almost identical. And therefore, data is almost symmetric, or if we were to draw this, would be normal or bell-shaped. This is how you would draw that. The other thing that I want to add, I want you to pay attention to this. What we have looked at here is a number of data which is even. What if it's odd? So for example, if this one, now it's odd, we are adding, I'm making up the data. I want to explain something to you because this question has come up before. So I'm just making up a number 103. And now, as you can see, instead of 1, 2, 3, 4, 5, 6, 7, 8, now we have 9 pieces of data. And clearly 87 is in the middle. And that is your Q sub 2. Now, what about Q sub 1 and Q sub 3? We cut this into 2 pieces. But the way it works, there are different approaches. But the main approach is to include this median or Q sub 2 with the bottom half as well as the top half. So if we keep it with the bottom half, Q sub 1 becomes 80. If we keep it with the top half, then Q sub 3 becomes 94. There are some cases and some statisticians who drop this, but this is the main one when the data is odd versus even.
If the mean of a set of data is 23.00 and 12.60 has a z-score of negative 1.30, then the standard deviation must be?
Well, we need to know the formula. As you know, formula sheet is available to you. Therefore, I hope everybody can find this in a formula sheet. Z equals x minus mu over sigma. And basically, you want to plug in. Since sigma is missing, the cross product will result in sigma being x minus mu over z. We are going to replace the values accordingly. So the x value is 12.6, the mean is 23, and the z-score was negative 1.3. When you calculate it, the answer becomes 8. Therefore, the answer is D. So it's a simple calculation using the z-score class. We are using the z-score to calculate this. X minus mu over sigma. What is it good for, the z-score? Find the z-score for each student and indicate which one is higher. When we have a case such as this one, we are dealing with art measure and theater measure, and we have different scales and we want to compare their scores. Therefore, we compare their z-scores. So the concept of curving, if you will. So we need to calculate the z-score for both measures, for art measure. So we plug in z is x minus x bar over s. If it's the sample, we use this formula. If it's the population, we use this formula. Either way is fine for this calculation. So if you look at the AM, short for art measure, x minus x bar, that means 46 minus 50 over s, that means 5. And you calculate this, you end up with a negative value of z minus 0.8. So negative 4 over 5 or minus 0.8. We do the same calculation here, x minus x bar over s, and that makes it 70 minus 75 over 7. And it gives us also a negative value. Now, I hope you realize, although both are negative, this one is larger than this one. And it gives us the answer C. The theater measure has a higher score than the art measure. What I want to add here, and this is important, generally speaking, the concept of the z-score is as follows. If the z-score is 0, that means the grade is equal to the mean of the class. If it's positive, the score is larger than the mean. And if it's negative, the score is less than the mean in class. So negative score doesn't mean that somebody is getting a negative score. It's just that it's less than the average in class. That's the meaning of it.
If the 5-number summary for a set of data is 0, 3, 6, 7, and 16, then the mean of this set of data is?
Well, in order to calculate the mean, you need to have all pieces of data. We don't have all the data. Therefore, we don't have enough information to do the calculation. Which of the following is true? The answer is B. Why is that? Let me give you a number of definitions. D stands for deciles. That's a measure that those are measures of location that divide the data into 10 equal parts. Percentiles, measures of location that divide the data into 100 equal parts. Quartile, measures of location that divide the data into 4 equal parts. Because of the definition, D5, P50, and Q sub 2, take a look, they are identical, therefore.
A student received the following grades: an A in statistics, 4 credits, an F in physics, 2, 5 credits, a B in sociology, 3 credits, a B in literature, seminar, 2 credits, and a D in tennis, 1 credit. Assuming A equals 4 grade points, B equals 3 grade points, C equals 2 grade points, D equals 1 grade point, and F equals 0 grade points, the student's grade point average is?
Well, here's the weighted mean, and that's how your GPA is calculated. So first and foremost, when different X data values are assigned different weights or W, we can compute a weighted mean. To find the weighted mean of a variable, multiply each value by its corresponding weight and divide the sum of the products by the sum of the weights. And we start with the grades. We know how many units. For example, A is 4. The next one is F5. The next one is B3. The next one is also B2. And the last one is D, 1 unit. So we know that. And we also know how much they are worth. A is 4 points, B is 3, so on and so forth. So we put them in front of them accordingly. For A, 4 points, for F, 0, so on and so forth. So we have to multiply these 2 columns and divide by the total number of units. So the formula is what you see here. Summation of WX divided by summation of W, the weights. multiply these two columns, divide by the total number of units. This is how your GPA is calculated. It's important for every student to know that. So we multiply 4 by 4, 5 by 0, 3 by 3, 2 by 3, 1 by 1. We add up those numbers. And normally GPA is given with a couple of decimals. I like to put more, but you follow the instruction as to how many decimals they're asking you to put in. We have the following data, and we want to find the value that corresponds to the 75th percentile. Well, this locator that I was looking at, if you remember previously, is going to help us here. Number one, rank the data. Number two, when we say 75th percentile, in essence means the 0.75 times the number of data give us the location. Therefore, in this case, 1, 2, 3, 4, 5, 6, 7, 8 pieces of data. And this locator k over 100 times n, that really means whatever this number is, 0.75 times 8. That's the meaning of this locator. So you don't want to be confused by this methodology. Simply 75th percentile means 0.75 multiplied by 8. The way it works, when it is a whole number, they go between that and the next one, 6th and 7th divided by 2. So number 1, 2, 3, 4, 5. This is the 6th one. This is the 7th one. Add them up, divide by 2. So the 75th percentile, the number is 50. For 30th percentile, we do exactly the same thing here. 0.3 times n, which is 8 in essence. 0.3 or 30 over 100 times 8 gives you 2.4. And we statisticians always round up. So the third one would be number 15. They always round up. And in this case, we are interested in finding the percentile corresponding to a specific number, for example, number 44, in which case the methodology is to look at the number of values that are less than that. So less than 44, we have those numbers. 1, 2, 3, 4, 5. How many? 5. So 5 out of how many? 5 out of 8. And that corresponds to the percentile. So simply put, change this to a percentage, becomes 0.625 or 62.5. P63, normally we rounded accordingly. If you wrote P62.5, there is nothing wrong with that. They just want you to round it normally accordingly. So 62.5 becomes 63. Finally, we want to use the range rule of thumb to estimate the standard deviation. I hope you remember when we did the range rule of thumb, we said mu plus minus 2 sigma or x bar plus minus 2s. So what does it mean? If you start from the mean and you go 2 standard deviations on each side, you cover about 95% of the data, which is normally good for everybody. And therefore, the whole range should be about 4 times the standard deviation. So the range is 4 times the standard deviation, or the standard deviation can be approximated by this division, range divided by 4, or divided by 4. And as you recall, range is max minus mean. So 72 minus 10 over 4 gives us 15.5. So this is the rough value for the standard deviation. Needless to say, we can calculate the standard deviation with the formula that we have.
The following data representing numbers of keyboards assembled for a sample of 25 days in a company. 45, 52, 48, 41, 56, 46, 44, 48, 40, or 53, 51, 53, 51, 48, 46, 43, 52, 50, 54, 47, 44, 47, 50, 49, 52, 42. Construct a frequency distribution table with 4 classes.
Let us rank the data. Now, there are 4 classes. So the way we calculate the width or estimate the width is to divide the range by the number of classes. Now, as far as the number of classes, when you're making up your own frequency distribution table, nobody's going to tell you, but normally you want to have it manageable. So in this case, it's 4. It's given to us. So the range is the max 56 minus the mean 41 divided by however number of classes. And if you keep at 3.75 may not work, you must round it to a nice and easy number. In this case, 4. You could work with 3.75, but it becomes a lot more difficult. So what happens is, first, you find the width. Now that we have the width, where do we start? We can always start with the smallest number or something a tad smaller than that, which is nice and easy to use. So the lower limit of the first class is a starting point that it's a convenient number less than or equal to the smallest value. In this case, is 41. So if we choose 41 as the first number, then with the width of 4, if I use 41, that means I need to add 4 to get to the lower limit of the next class, and another 4 to get the lower limit of the next one, and another 4 the next one. And because this is 4, you can add 4 to 41 and subtract 1, because if you recall, when we have one class, the upper limit minus lower limit plus 1 unit, that's how you would set it up. Therefore, we have the following. Again, we have those numbers. And for this one, you can say upper limit minus lower limit plus 1 unit. If you want to go with that process, this actually the way you find 44, upper limit minus lower limit plus 1 unit is the width. And if you replace the lower limit with 44 and the width with 4, you get 44. And of course, as you can see, this way we are adding 4. So what about the frequency? You really have to go and figure it out here. 41, this is all the way to 44. So 1, 2, 3, 4, 5. For example, right here, you would put 5. That's why ranking it is truly a must, and it's helpful. So one easy way, just write those numbers, 41 to 44 counted, 45 to 48, and now you can fill up the table. Many times we just do the tally. In other words, 41, we put a tick mark, and 42, another one, and another one, and then we count them. Either way, come up with the proper number of frequency for each case, and the first one is 5, you can figure out the rest. So that is the frequency distribution table. Now we are interested in using that to find the mean. First, we are going to find the data by using the data to find the actual mean, which is summation of x over n. So x bar is summation of x over n. We add up all the numbers that we had from 45 all the way to the last one, which was 42. And we divide by the total size of 25 or n. And that gives us the x bar. This is the precise mean from the total data that is available to us. So how do you calculate x bar? Summation of x over n. Just plug in, add them up, divide by size. We can also use the frequency distribution to find the mean. This is in case we don't have the actual data, the original data. Normally, if you have the original data, you don't go there. But I just want to show you that this part is true, or the two means reasonably close. That's what I want to discuss. So here's how it works. You want to calculate the mean by adding everything up, dividing by size, but you don't have the individual piece of data. That is the assumption here. So how would you calculate the mean? If you look at, for example, the first class, maybe all of them are 41, maybe all of them are 44, or somewhere in between, we don't know. So what they do, they actually say, let's assume all of them are in essence are equal to the midpoint of that class. So they add up these two, 41 plus 44, and they divide it by 2, they get 42.5. They get the midpoint here. They get the midpoint for the rest of them by adding the width. And then they use the formula summation of f times x sub m over n. So they multiply the frequency by these midpoints that we came up with, where x sub m is the midpoint of each class. So let's add them up, divide by 2, and notice as long as you calculate one of them, then all you have to do, add the width, 4, another 4, another 4. Now, to do this, we are going to multiply this column by this column. In other words, 5 times 42.5, 8 times 46.5, 8 times 50.5, 4 times 54.5. Add them up, divide by n. N is the same n 25, because even if you don't have it here, you can add up those numbers, and they give us n equals 25. When we go through the process and we calculate this, we end up with 48.26. So take a look at the actual mean calculated in part B, the exact mean, versus the one we just came up with. That's pretty good. So they are reasonably close.